Actually, I didn't know what is the public lecture, so I assumed that it is supposed to be intended for students. So I have decided to speak about this subject, and actually, okay, this is about events which happened like 30 or 40 years ago, and actually I was a student at the time. And these events, right now, you can survive without knowing what is the ellipsoid algorithm, okay? But as it happens, historically, the advent of this algorithm was a very important event, and it triggered, in fact, the revolution in optimization science, which resulted in what we know now as modern optimization, okay? So this is really intended for students, and old people can just, well, look in their laptops, I don't know. Okay? Okay, so the objective is to solve an optimization problem, which is convex optimization problem. Okay? So we want to minimize the function, which is convex and continuous, on a convex and bounded set. All right? This is it. This is a generic problem we want to solve, and actually the ellipsoid algorithm is the method to solve this problem, okay, with linear rate, meaning that if you need that the accuracy of your solution, you will get when this convergence ratio, which is 1 minus 1 over n squared, n is the problem dimension, the dimension of control variable x. So it means that each n squared iterations of the method, you add a new significant digit in the accuracy of your solution. Okay? So they speak about linear rate of convergence. There were really significant developments due to this algorithm in computer science and optimization. In particular, the ellipsoid algorithm was used to prove the famous result about polynomial solvability of linear programming. And there were also computational results about it. And actually, for small n, this is a quite good algorithm to solve convex optimization problem for relatively small dimensions, like dozens. All right? Computational also, this algorithm is not good if you are in high dimensional situation. But in some sense, this algorithm triggered the development of what is now known as interior point algorithm, which are maybe the most advanced, in a sense, algorithms of optimization. And actually, even new algorithms which are used for extremely large scale optimization problem, they have some internal machinery and which can use ellipsoid method. Okay? So once again, our goal to solve the very basic optimization problem, minimize the convex continuous function on a bounded and closed convex set, a compact convex set. Let's say we are in Rn, all right? And what we would like for a non-empty interior of the set. So such sets which are bounded, convex, and closed with non-empty interior, we will say that these are solids. Right? So what we want, what the algorithm is in, this is an iterative algorithm. Okay? And the information which is used about the problem will be as follows. It's formulated in terms of oracles, okay, which is a useful abstraction here. So what we need, so imagine this is the feasible set X. Okay? We need the separation oracle. The separation oracle is the following. So suppose you have a point, small x, which is, small x, which is outside the set. What we need a linear form which separates x from our feasible set. So you see that the value of this linear form at x is larger or equal than the value of this linear form on all points of capital X. Okay, this is the separation oracle. And what also we need, this is the first order oracle for the function f, for the objective. So if we choose a point x, okay, inside this set, then we need the first order oracle, which provide us the information about the subgradient. Okay, if you don't know what the subgradient is, just think of plane gradient, okay, of the objective. And it provides us the information about the value of the function at this point. Okay? So, of course, when you solve an optimization, a real optimization problem, you have to compute this information. You have to access this information about the function, but this oracle abstraction is quite useful to speak about iterative algorithms. Okay? Okay. And what we will require also is just saying, well, this is not really obligatory, but for what follows, we will say that basically we know that there is our set, capital X, is included in a big, relatively big Euclidean ball, say of radius R. Okay? And of course, since we assume that X is solid, there is a small Euclidean ball which can be inscribed in capital X. Okay? So these are the assumptions under which we will work. An example. Okay? So look at this problem. If you know what is linear programming, I address young people. Who knows what is linear programming? Okay, fine. So this is just a linear programming problem, okay, which is written in quite strange form. So you have the objective, which is the maximum of linear functions. Okay, so our function f is just the maximum of linear forms like this. So the function itself is the function like this. So this is a convex function which is not differentiable, basically. Okay? So it's just a strange way to write down a linear programming problem which is below. So what we will assume that the feasible set capital X, which is described by these linear inequalities, so in the description of this feasible set, there are no vectors A, okay, in the inequalities which are 0. Okay, because just if we have like this, so we will remove them. It doesn't change whatever the behavior of the problem. Okay, so now what will be the separation oracle for this? So our feasible set is just a polyhedral set. Okay, so it's described by the inequalities AI transpose X less or equal than BI. So if we have X, a point X, we will verify if all the inequalities are verified. Okay? And if they are not verified, we will take the inequality which is not verified by X. So let's say that there is AJ transpose X which is larger than B. Okay? And it's clear that for this, the linear form AG with vector AG will be the separator. So the value of this linear form at X will be larger than, of course, the value of this linear form at any point Y, which is in capital X. Okay? Now, if we want to compute the first order oracle, so we need the value of the objective and the subgradient of the objective at point X, which is in the feasible set, it's also very easy. Okay? We just find the linear form which is really the maximizer, at which the maximum is attained, and take the coefficient of this linear form, the coefficient vector of coefficient of this linear form is the subgradient, and the value of this linear form is the value of the function. So in this situation, it's cheap, computing the both oracles. Now, what is the ellipsoid algorithm? How would we solve the problem? Just to understand the logic behind it, let us consider a very simple case of one-dimensional convex optimization. Okay? So we have a segment AB, and we want to minimize the convex function f on this segment. All right? So what we would do bisection. So the idea is the following. We start with some localizer. Okay? We have initial localizer for our optimal value, which will be delta 0. Okay? And we will look at the middle point of the localizer. What can happen that this middle point of the localizer, it doesn't belong to our feasible set. Then, of course, we will be able to take the half of the localizer in this situation, right half of the localizer, and the other situation, the left half of the localizer, which will contain the feasible set. Okay? So now we reduce by factor 2 the length of the localizer, and we lose no information about our optimal solution. The same if we are inside the middle point of the localizer is in the feasible set, then we can look at the gradient of the objective. Okay? In situation 2a, it's clear that all points on the right on the left of the medium point of the segment, they are of no interest. They do not contain the optimal set. Okay, so we can cut it, we can just throw it out, and we divide by 2 the length of the localizer once again. And actually, in this situation, for instance, so we have this left modification, right modification. If by chance, actually, the oracle said that the value of the subgradient was 0, we have found the optimal solution. Okay, so this is the idea of the bisection algorithm, which is the simplest algorithm of convex optimization, but actually this is very efficient because it converges linearly also. With a factor, it converges with a factor 2. Now, how we can generalize the idea of bisection in multidimensional situation? This is what they call Khachiyan plane scheme. Okay, so now imagine we have our feasible set, which is the black set. Okay, and we have our current localizer, which is the blue set. Okay, at some point of the localizer, if we are in the feasible set, we will measure the gradient. Okay. Imagine that in this situation, the gradient points in this direction. And it's clear that this this part of the localizer, okay, doesn't contain the minimum. So we can, once again, we can throw it out. Okay? If we are outside the feasible set and we have this point, and we have the access to the separator, once again, if we have the separator, we can throw out this part of the localizer. Okay? This is the idea of a Khachiyan plane scheme. So instead of just using the we don't only need instead of using just in bisection, we have plus or minus. Here we will have the direction of the gradient or direction which is given by the separator. All right, so the first realization of this, the first efficient realization of this Khachiyan plane scheme, it was center of gravity method, which is of theoretical interest, but it's very nice. It's based on very nice ideas. Actually, so the idea is the following. We start with the initial localizer, which will be our set capital X. And then we put the search point in the center of gravity of the current localizer. Okay? And if the search point is outside our feasible set, okay, we pass the separator by the search point and throw out a part, in this situation, it's always in the feasible set, of course. Our first localizer is capital X, so our all search point will be an X. So we put we look at the value of the subgradient at the center of gravity of our localizer, okay, and then do the cut of the localizer. Okay, so basically the idea is, so we have our current localizer, which will be GT, okay, we take the center of gravity, which will be the next search point. And we look at the value of the gradient. And then we will do the cut. So with this, we can throw out, so the new localizer, which will be GT plus 1, will be this half of the previous localizer. Okay? And as an approximate solution after T iteration, we will take the best search point so far. So the search point at which the value of the function of our objective, because we have access due to the first order oracle, we have the access to the value of the objective, so we just take the best search point. Okay? And there is very nice theorem which is due to, the very nice result which is due to Levin in the USSR and Newman in the US, and actually which says that, look, what will happen, and this is very nice result of convex geometry, so the volumes of the localizer, so each time we do the cuts, we are guaranteed that the volume of the localizer will converge very fast, will converge linearly with this ratio. And this is highly non-trivial fact. So as a result, actually, due to this convergence of volumes of the localizer, it happens that the objective will also converge fast. Okay, so it will be the rate of convergence of the volumes to the power 1 over n, 1 over dimension. Okay? And this is a beautiful result, which is known as Green-bound theorem in convex analysis. And basically, you can think of the game like, imagine we have a convex pi, okay, and we will play the game. I will give you the vector, which is the direction of the cut, and you have to choose the point by which you have to pass the cut corresponding to this direction, okay? And I will take the largest part of the cake, okay? Now, what is the maximum volume of the cake you can keep for yourself? How should you choose the point to get the maximum part of the cake? As it happens, it should be the center of gravity of the cake. Okay? And basically, this is something really non-trivial, and it's really related, this ratio. So I know that the maximum part of the cake I can have, or you know that the maximum part of the cake you will give me, there will be like this n divided by n plus 1 n divided by n plus 1 to the power n. So the higher is the dimension, the smaller will be the ratio of the volume, actually, of the cake you will give to me. And the reason for this fact is what they call Brown-Minkowski inequality. So with Brown-Minkowski inequality, it says that the average diameter of the convex set is a convex function. Okay? And as it happens, this result was proved by Brown and Minkowski. It was, 880, something like this. So, by the way, Minkowski, he was the father of convex analysis. He invented even the word convex, basically, I believe, is due to him. So, calling these sets convex sets. And as it happens, actually, the convexity of U and V, the convex set, is really redundant. It even works for non-convex set. And actually, the proof passes by Minkowski symmetrization principle. And it's exactly the previous result. So imagine you have a convex set. Now you choose the direction, and you symmetrize your convex set around this direction. So what you say, okay, I will choose the direction, and I will do the cut which is orthogonal to this direction, and I will make a body such that its cross-section will be the disks with the same exactly volume as the cross-section of these convex bodies. Okay? And this result says that this symmetrized body will also be convex. Okay? And this is exactly the convexity of average diameter. Okay, as it happens. So this is very nice result of convex analysis, and basically the interest of this center of gravity algorithm, barycenter algorithm, is related to this. So this algorithm was discovered in '65, and basically one could ask what was the impact of this discovery on optimization. And actually there was none. And the reason for this is that computing the center of gravity of a complex polyhedral set, it's hard. It's difficult. We don't know when the number of cuts, actually when our polyhedral set is defined by a large number of cuts, even in small dimensional situation, it's very hard to compute the center of gravity. Okay, there are some random approximation which can be used and so on, but deterministically we know that this is a hard problem. So just this problem which should be solved at each iteration of the center of gravity method, we don't know how to solve it efficiently.
Is that a combinatoric problem?
Yes. Yeah. So I will talk a little bit about combinatorics later, okay? So how can we save this cut-in plane scheme? And one of the idea is, what is the problem of the center of gravity method? Each time we do the cuts, we complicate our localizer for the minimum. And the idea is, let us try to stabilize the geometry of the localizer, okay? So let us try to be the same, let us try all the localizer have the same geometry. And the idea would be, let us try to have the localizer in the form of ellipsoids. So how could we realize this idea? So this idea was the idea, by the way, of Nemirovski, and it was, I think, it was invented in '76. So just let us recall what is the ellipsoid. So the ellipsoid, we know this is the level set of a convex quadratic form. Okay? Another more productive, in our case, vision of the ellipsoid is just the affine image of the Euclidean ball. Okay? So you do just the linear transformation of an Euclidean ball, affine transformation of an Euclidean ball, and you obtain an ellipsoid. Okay? Now, if we assume that the volume of an Euclidean ball is just 1, okay, then the volume of the ellipsoid is just the determinant of this matrix B. Okay? Of course, between two representations, quadratic form representation and image of the ball, we can easily recompute all the parameters. All right? Now, what is the idea of the ellipsoid algorithm? So imagine that at some point we have the localizer, which will be an ellipsoid, which covers the optimal set of our problem. Okay? Now, we use the separation oracle, or we use the first order oracle. We do some cut, and we cut our ellipsoid. All right? So our ellipsoid E, we do some cut, which passes, of course, by the center of the ellipsoid, and we don't know a priori, we don't know what could be the direction of the cut. The only thing we know, it will pass by the center. Okay? And our new localizer will be this E prime for the minimum. Sorry, we know that minimum will be in this part of the ellipsoid. It's half of the ellipsoid. What we will do, we will just try to choose new localizer, which will be the smallest volume ellipsoid, E plus, which contains E prime. This is the idea. Okay? Now, the beauty of the fact is that you can easily compute this new localizer. Okay? So it's not very complicated to compute the ellipsoid, which will contain the half ellipsoid, whatever is the half ellipsoid. And the trick is very simple, because the ellipsoid is in a affine image of an Euclidean ball. Okay? Let us go back to the Euclidean ball. And actually, imagine this is the cut of the ellipsoid, okay, which we want to put it into the ellipsoid of the smallest volume. Now, we do the inverse transformation to obtain the Euclidean ball, okay? We cut this Euclidean ball in the way we would like, and just the half ball. And we cut the half ball with the ellipsoid of the smallest volume. And this is just analysis. It's really not complicated because of all the degrees of symmetry. There is just one variable to be optimized, and okay, this is easy. Okay, I can do it. I mean, after doing 10 times, you eliminate all the errors, so it's really not complicated. Okay, now what is the ellipsoid then? So we initialize our procedure with a ball of big diameter R. Okay, and now we iterate. Okay, so each iteration we have the localizer, which is an ellipsoid. We do the cut. Okay, so there are two possibilities. The center of the ellipsoid, the barycenter of the ellipsoid, will be inside the feasible set. In this case, we will say that this step is productive, the iteration is productive, and we will do the cut according to the gradient of the objective. Okay, if the center of the ellipsoid is outside of our feasible set, then we'll say that the step is unproductive, and we'll do the cut due to the separator which we have. All right, and then we will cover the half ellipsoid which we obtain with an ellipsoid of the smallest volume. This is just the idea. We iterate this way, and basically we choose the approximate solution, same as before, just the best search point so far. The best with respect to the value of objective. So this is just a very simple example. So we want to minimize just a quadratic form, and this is the optimal solution, the optimal value, and the optimal solution is just the lower right corner. Okay, and we start with this initial ellipsoid, which is the circle 0, and we iterate, and you see what happens, how the ellipsoids decrease. So if you look at this, you basically see that each time, so when you double the number of steps, you double the precision. Each time you double the number of iterations, you double the number of significant digits in the precision. Okay? So this is the accuracy result about the complexity, what they say the complexity result about our ellipsoid algorithm. which says that after t iterations, you will have an epsilon solution. You will find a point inside the feasible set which is close to the optimal value, such that f of xt is close to the optimal value by this epsilon, if t epsilon is of this order. So what you see there is this factor, this big R divided by small r, which is inside. And okay, basically there is, I have put it just because the proof which follow uses this, but it's just for technical reasons. Basically there is no this stuff like this, but anyway, this ratio is on the logarithm. Okay, so it can be millions, but this will be just a constant. And here you see what you can call the relative accuracy. So here is the variation of the objective on the set, and divided by the precision we want, and it is also under the logarithm. We call this the linear rate of convergence, stuff like this. So when you do, each time you do n iterations of the method, okay, you improve your accuracy by the factor, say, of 2. Okay, n is the problem dimension. Wait, I will basically skip the proof. Okay. And okay, if you are interested, you will find in the slides. It really takes a few minutes just to see through it. And I will talk about some very nice implication of ellipsoid algorithm, which is this result about polynomial time solvability of linear programming. So if you know a little bit of computer science, in computer science there are classes of complex, difficult problems. And at some point in the 70s, people discovered that all difficult problems in computer science, they are actually, basically they are the same. Okay? So they used the notion to define the difficulty of a problem in computer science. They used the notion of P and so on. So in computer science, you describe the problem by the size of the problem, you describe it by binary length of its description. Okay? And actually, they say that the problem are the non-deterministic polynomial if I will exhibit a solution to the problem, you can easily, in polynomial time with respect to the length of the description of the problem, you will be able to verify if it's a solution or not. So typically, the problem is like this. The answer is yes or no. Okay? So if I exhibit the solution, it will be easy to verify. On the other hand, if I give the problem, it may be difficult, we don't know, it may be difficult to find the solution, if the solution exists. Okay? So in 70s, people discovered that there are these hard problems, there are simple problems, which they call polynomial, for which finding a solution, or saying that there is no solution, just take polynomial time in the length of the description. Okay? And there are difficult problems. There are few problems, 2 or 3, for which the status was unknown. Okay? And one of these problems was problem of linear programming. So since in P and P, so the problem should be yes or no. Okay? For instance, you can think if a linear problem, so and the description of the problem should have finite length. So let us think of a linear programming problem like this, with rational coefficients. Okay, and for that matter, basically, we can assume that the coefficients are integer. Okay, and the idea, what we want to understand, for instance, if this problem has a solution or not. So this is the question. So we don't think for the solution in integer variables. Okay, the description of the problem is, we have integer coefficients, but the solution may be, whatever, rational. Okay. And actually, okay, so let us look at this problem, which is basically perfectly in this in P thing. So we have a linear problem with integer, with matrix A and a vector B, which has integer coefficients, okay? And what we want to understand if this problem is feasible or not, if this problem has a solution or not. We want to answer this question. So the question is, if we're able to do this in polynomial time with respect to the length of the binary description of this problem. And as it happens, this problem is polynomial. This can be done in polynomial time. And the proof is very nice and very simple. And I cannot refuse myself just to present it here, okay? So what we will start, we will assume that in R, the coulombs of R, they are linearly independent. If you think the linearly dependent coulombs, they don't change anything. I mean, they don't change the span of A, so the solvability equation of solvability of the system of inequalities, it will not influence it. Okay, so we can just eliminate all the linear dependent coulombs from A and assume that all coulombs of A are linearly independent. Okay, so we will assume that all the coefficients are integer. Okay, and we will reformulate our feasibility problem as an optimization problem. Look, what does it mean that all AX or all equations, we have equation A transpose X less or equal than B, A transpose IX less or equal than BI, where A transpose I are just lines of the rows of A, okay? So they all should be less or equal than B. So it means that, okay, AX minus B, if this guy is solvable, then this maximum, there is X such that this maximum is negative. And if the problem is not solvable, then this maximum will be positive. And this is the convex optimization problem, okay? So now, instead of saying, okay, the system is solvable or not, we can just answer, we have just to answer the question, if this optimization problem, its optimal value is less than 0 or larger than 0, okay? If we're able to do this, we will answer the question of solvability. So let us use the ellipsoid method to solve it. Okay, this is the idea behind. We will use the ellipsoid method to solve this problem, and we will look at the optimal value obtained by ellipsoid method, and we will say this problem is solvable or not. However, there are two questions. Okay, ellipsoid problem basically works with bounded sets, and here the domain is Rn, is not bounded. Okay, and actually we know that ellipsoid method will give us the solution with certain precision. Apparently, basically, we have to answer the question: this optimal value is less or equal than 0 or strictly larger than 0, which is just we need infinite precision. Hopefully, and this was proved by Khachiyan, this is a very nice piece of mathematics and quite simple. Actually, if the original problem, if the solution of the original problem is negative, the optimal value of the original problem is negative, then the solution of the bounded problem like this, so L is the length of binary description of our problem. Okay, so we can bound the value, the norm of our solution, just look for the solution of this norm. If the original optimal value is negative, then non-positive, sorry. This one will also will be non-positive. And the proof is just the convex geometry. So it says, okay, so we have assumed that there are no linearly dependent coulombs in A. It means that the polyhedral set like this does not contain lines. Okay? The polyhedral set which does not contain, the convex set which does not contain lines has extreme points. Okay? So, if there is X for which this AX is less or equal than B, then there is an extreme point of this polyhedral set for which it will also be verified. It will also be non-positive. So we can look for extreme point of this set, and if you remember, if you know the characterization of extreme points of polyhedral sets, so say we have a polyhedral set, and this guy and this guy, these are extreme points. Okay? So the characterization of extreme points of a polyhedral set is that these linear inequalities, say we have linear inequalities defined by vectors A1, A2, and so on. So exactly n in the dimension n linear inequalities are equalities at these points. This is characterization of extreme points of the polyhedral set. Okay, so we have a matrix, a submatrix of size n times n, A bar of A. We have a subvector B bar of B, such that at all extreme points, so for each extreme points there are different, of course, subsets and so on, but we have this equality. Okay, so extreme point is just a solution of such a system. Now, the components of the solution to this system, okay, of course we can use the Cramer rule. It will be the ratio of determinants. So determinant delta is the determinant of A bar, and determinant delta G is the determinant of the matrix which we obtain from A bar by substituting the G coulomb by vector B. Okay? Oh, sorry. Okay, and basically now we are done because look, the matrix A bar has integer value and determinant is non-zero, it means it's at least 1. Okay, the denominator is at least 1. Now, the determinant, which is in the numerator, is also bounded, in fact, by 2 to the power L, because there is a nice inequality of Hadamard, because the determinant is a volume. Okay, and there is the Hadamard inequality, which says that the determinant over parallelotop, okay, is just less or equal than the product of length of the edges. Okay, so in matrix formulation, it means the determinant of the matrix is less or equal than the product of length of the coulombs. And of course, the length of the coulombs, because the description of the whole matrix is the length of description is bounded by L. Actually, the length of the coulombs are bounded by L. All the length of the coulombs are bounded by L, so the determinant, as it happens, is bounded by 2 to the power L. And then we obtain that all the extreme points of this set, they will be bounded. Their components will be bounded by 2 to the power L. So instead of looking at the original problem, so to verify if the optimal value of the original problem is negative or not, we can just look at this bounded problem just to verify, trying to get the answer for bounded x's. Now, there is also the problem of accuracy, okay? Now, the second result says that if the optimal value of the problem is positive, it cannot be too small, okay? It will be at least 2 to the power minus 12. And you obtain it exactly in the same way. So actually, our linear programming problem we have there, okay, we can rewrite it in this way. Right, so our minimization problem, it's exactly minimizing t such that ax minus t times vector of all the ones is less or equal than b. Okay? Now, if the optimal value of this problem is positive, then it means that the solution set of the problem, the feasible domain doesn't contain line, because if it contained line, then going along the line, we would get minus infinity. And we know that we assume that the solution is non-negative. Okay? Sorry, it is positive. So if the convex set, if the solution, the feasible set does not contain line, of course it contains extreme point. And we know that the optimal value is attained at the extreme point of the polyhedral set. And now once again we have to compute, we can use the trick when computing the extreme points, and we see that for all the extreme points, okay, now when we will resolve our system describing the extreme points of the set, we will have in the denominator, we will have the determinant, which will be 2 to the power L because actually 2 to the power 2L because the description length of these guys is bounded by 2L. Okay? And in the numerator, we will get the determinant, which is at least 1. Okay, so this ratio will be 2 to the power minus 2L. Okay? Now, what we come to, look, now we have to solve the problem like this. We have to answer the question. We have an optimization problem, which is perfectly in the realm of ellipsoid algorithm, and we have two hypotheses about the objective value. Either it's non-positive, or it's larger or equal than 2 to the power minus 12. Okay? And to answer to decide between these two hypotheses, it suffices to solve our problem to accuracy 1/3, okay, times the gap between the two. Right? So let us use the ellipsoid algorithm to do this. Okay? And actually, when you look, because of this linear convergence of the ellipsoid algorithm, actually the number of iteration will be proportional to L. And at each iteration, we will do some simple linear algebra, which is also operations which will also cost us L, order of L arithmetic operation, and so on. So we will finish with something which is proportional to, which is polynomial in L. There is a slight point because we were talking about here, when we were talking about ellipsoid algorithm, we were talking about real arithmetics. And basically here we have to use final precision arithmetics, but fortunately ellipsoid algorithm it's stable with respect to rounding errors, and it's, okay, it's tedious, but it's easy to prove that actually using finite accuracy operations, we will also obtain the same result. Okay? Okay, basically from deciding about solvability or non-solvability of a linear system of inequalities, you come to solvability of linear programming very easily. So, okay, I will skip probably this. Okay. Just two final remarks. It was very nice what happened. So for this work, Khachiyan, Nemirovski, and Yudin received Fulkerson Prize in '83. And they also received the publication in New York Times. And the publication was very strange because the publication said, okay, linear program is polynomial solvable, what means that communist economy, socialist economy, they can optimize everything now. Okay, so essentially it means that socialist economy will outperform capitalist economy which doesn't use optimization. Okay, it was 83 or maybe 84. Okay, and 5 years later, the Soviet Union ceased to exist. But it was not related to ellipsoid algorithm. What was related with ellipsoid algorithm, actually, that it's polynomial. Yes, people used it to prove the polynomial solvability of linear programming, but the problem with ellipsoid algorithm, that it works exactly as it predicts. Okay? So if you want to solve a linear program with 100 variables, you still can use, if you wait enough, you still can use ellipsoid algorithm, but for large dimensional linear program, it will not work. But what happened, as soon as people knew that linear programming is polynomial solvable, it resulted, Karmarkar is like in 6 months he developed a new algorithm which was completely different with respect to everything which existed, that he proved that which was also polynomial. Okay, few months later he proposed another algorithm for which he could not prove the polynomial convergence, but which was very fast, and it was one of the first algorithm of interior points algorithm. So it triggers some sequence of events which actually completely changed the face of optimization. So just the second remark to finish without it. So why ellipsoids? So we said, okay, we will so the idea was to keep the geometry, so to stabilize the geometry of the localizer, and to this end we will use the localizers as ellipsoid. Basically, the property which we use of ellipsoid is like this. So we have a set Q. Okay, now we do the cut passing by the center, say, of the set. So then whatever center of the set, we obtain a half set Q prime, and now we want to put this half of the set in the set of the same geometry, which is an affine image of the original set. Okay? And we want the determinant of this matrix B, of this linear transformation, to be small. The smaller is this determinant, the better will be the rate of convergence of the algorithm which we will obtain. And basically there are other sets which possess this property. The first algorithm which was proposed using this idea was Simplex algorithm. So outscribed Simplex, basically for this algorithm, you obtain slightly worse rates of convergence. You can also use the hybrid of the outscribed simplex and ellipsoid. You can use the spectrometer and so on. And in theory, okay, in theory, they are slightly worse. Instead of this factor n to the power 2, you basically have n to the power 3. Okay? The difference is that in practice, actually, it's quite different because the ellipsoid, actually, this rate of convergence 1 minus 1 over n squared, it doesn't depend how the cut passes. Okay? Basically, whatever the cut will be, the ratio for the ellipsoid will be 1 minus 1 over n squared. And actually, for simplex algorithm, for outscribed simplex algorithm, it may be much better depending on the direction on the cut. And in practice, people use they use simplex algorithm, this outscribed simplex algorithm, because in practice it works better. There is another algorithm which is completely different, but which also uses the same ideas, and this algorithm is due to Khachiyan and Tarasov, and the idea was the following. The localizers which we obtain will be still obtained by the cuts, okay? But the size of these localizers, we will measure it by the volume of the largest volume ellipsoid inscribed in the localizer. Okay? And as it happened, you can show that the volumes of the inscribed ellipsoids will go fast to 0, and the rate of convergence of the algorithm will also go fast to 0. So basically, this algorithm has better complexity estimate. It's n instead of n squares for the ellipsoid algorithm. The problem is that actually computing the largest volume inscribed ellipsoid, it's what they say, it's tractable problem. Okay, so in fact, for a polyhedral set, it's just a semi-definite optimization problem, but it's much computationally demanding than computing an ellipsoid. And this algorithm, basically, I don't think it's used in practice. Okay, I'm done. Thank you very much.